Well, good morning, and welcome to the 2015 Sverdrup Visiting Scientist Lecture. So this event is made possible by generous donations from the Sverdrup family and some support from the NASA Space Grant Fund. There are two goals for the Sverdrup Visiting Scientist program. First, to provide an opportunity for Augsburg students and faculty to interact on a personal basis with scientists of national stature. Second, the program provides an annual forum where the whole Augsburg community, including our neighborhood, has an opportunity to expand their knowledge on a science topic of national significance. Today's event is also part of the Convocation series here at Augsburg. And the Convocation series asks us to consider the power of vision in a world of tension. It also offers us a time to come together as a community and hear outstanding leaders and visionaries who join us to discuss making the world a safer place for future generations. Now, this series this year included titles such as Historical Consciousness and Black Feminist Imagination and Urban Faith-Based Activism. So today, as we talk about the atmosphere, let us consider that issues of peace or social justice are actually connected to the ozone layer in our atmosphere. And we could, of course, note that now more than ever, we're forced to consider that the quality of our collective human existence is impacted by the physical state of the planet. And that by studying the Earth's atmosphere, we are indeed making the world a safer place for future generations. This year's Sverdrup Visiting Scientist is Dr. Ann Douglas, who joins us from NASA Goddard Space Flight Center, where she is a senior scientist and currently the project scientist for NASA's Aura satellite mission. Dr. Douglas is a nationally recognized atmospheric scientist and a leader in her field. And we've also heard this morning a mother of 5 and a grandmother of quadruplets, and the number goes even bigger. She started, for the students, of course, it's nice to imagine that she started somewhat like you at a small liberal arts college in D.C. studying physics. She made her way to the University of Minnesota, where she completed her master's degree and finished her PhD at Iowa State. During her distinguished career, she has earned numerous national and prestigious awards, recognizing her many achievements, including the fact that she's a fellow in both the American Meteorological Society and the American Geophysical Union. NASA has recognized her for both her exceptional scientific achievements as well as her outstanding leadership. This morning, she will discuss her life and career as an atmospheric scientist as she finds her way through the ozone layer. Please welcome Dr. Ann Douglas.
Thank you. And I wasn't going to take that really big step, although the introducers seem very comfortable with it. So it's really nice to be here. I just wanted to start out with a few things about who I am and how I got to be where I am, because I've actually had to reflect on that to figure out how it all happened. So I am the Aura project scientist, and I used to be deputy, and I was deputy for the Upper Atmosphere Research Satellite before that. And I'm also co-lead for the chemistry climate model at Goddard. And this is a really nice relationship, and I'm going to talk to you about the advantages of being involved in a satellite program and a model at the same time. And I wrote many, many papers, more than 150. And I am a fellow, which is really cool. I did never think I would be a fellow. I've been married for a really long time. My 5 kids are all grown up, and they all pay taxes, which is, I think, as good as you can hope for. And they have wonderful careers, and they're just really nice people in general. I do have 11 grandchildren, and 1 more coming soon. And I do have quadruplet grandchildren. And if you want to know who the stars are in my universe, those are the stars, my children and my grandchildren. No two ways about it. I was a Girl Scout leader for more than 20 years. It's one of the most fun things I love to do is take city kids out camping for the very first time, or get them onto a horse, or up a mountain. It's great. And I have a lot of hobbies. Yoga, I'm a whole inch taller than I used to be. This is true. You can ask me about this. And I love dancing. I think the world would be a happier and safer place if everyone went dancing Saturday night. Everyone. You can think about that. That's what I think. I also think that you don't really escape from the world that you grew up in fully. And so when you think about your life, you have to think of all the things that happened. So, yeah, I have got a little timeline up here of a bunch of things that happened during my life that got me to being where I am now, starting with Sputnik, which was a really big deal. I'll talk about that a little bit more. But the women's movement mattered. I, in fact, highlighted a few things which maybe you can see. Sputnik, the silent spring, so the start of the environmental movement, the feminine mystique, that I made a big decision in 1975 after I left Minnesota and moved to Iowa, and finally got my PhD. And you see I've got the diplomas and the babies and all the things happening all the time. It certainly wasn't a straight line. So what did Sputnik mean for me? It meant that I got to learn the new math, that in chemistry I got to observe a burning candle, and I'm going to guess maybe there's no one here who did chem study and observed a burning candle besides, aha, yay, chem study. It was a special time. And also that my dad used to tell me all the time, if you learn math, you can do anything. And that is actually true. The silent spring was what started the environmental movement, and we know many things have happened since then. It's not a picture of me and my sister, but it could have been. We were dusting all the time. And I say this to people, and I'm really serious about it. I was raised with no expectations, none. Whereas my daughters were not. My daughters were raised with high expectations. But in a way, that made my life a lot easier because it's when you go for your performance review, people want to know if you met or exceeded expectations. And if they have none, then you exceed them. It's really great. It made life a little easier. But my mom did take a full-time job to send me to a better college, and that mattered a lot. I studied like a maniac when I was in school because I realized I had been given a privilege that many, many people do not get. And when I was at school, my professors really relentlessly pushed me towards graduate school. So my dad was the first in his family to graduate high school. His other brothers and sisters had to drop out at 12 to take jobs. His dad had died. And so my parents really taught me to value that education, and that is one thing I've really tried to pass to my kids. So the decision came. I was idealistic. That ask not what your country can do for you made a big impact on me. I had moved to Des Moines because my husband was on the faculty at Drake, so now I'm commuting. So I gave up the lab work. I was expecting my third baby. I was the only woman graduate student. I had to figure out what to do. I thought I was going to do solid state there, and I just hated it. And I met a really nice, very smart person, John Stanford, and he just lured me into atmospheric science. And I thought, this will be great because I'm going to use my physics background to do something that matters. And so that was pretty cool. Originally, even in atmospheric science, I still wanted to teach. The concept was that I would work with physics and environmental science, and I would stand out as an applicant. The reality was that when you say you have 4 children and are looking for a 3/4-time position, people throw your application away. In fact, I've met people who told me they threw my application away. And the fun part of that is that they all regret it. Ha ha. And we had the two-body problem because my husband's a chemist and we had to find a job for both of us. So we moved to Washington, D.C., and I ended up meeting some people at Goddard and getting a job there and finding out that I really liked doing research and working in the satellite programs as much as I ever thought I would like teaching. So I've made a career doing that. And they also let me work part-time, and there was a lot of good stuff about that. So I've been involved with these satellite programs through my career. Why do they do the satellite program? Scientists say we need to predict. If we're going to predict and reduce uncertainty in assessment, I can't tell you how many proposals I've read from people who say, this work will reduce uncertainty in prediction, okay? That's what everybody says. Well, that's why they gave us the data, and that's why I feel like we have to use it. We can't be asking for data to reduce uncertainty in projection and then not do it. You have to do it. So, on the timeline, the ozone hole, 1985. And of course, nobody really knew that that was going to happen. It was a big surprise. There was immediately a big response, ground-based measurements, aircraft observations, and UARS was delayed by the Challenger disaster. It was originally supposed to go up in like 86, but because of the Challenger, they had to retool some of the instruments, and of course, they didn't fly anything for a long time, and it didn't actually go up until 91. So you didn't have a good satellite in the air at that time. But you had a lot of questions. Why the southern hemisphere? What's the hemispheric impact? What's the year-to-year carryover? What are you going to do? What's happening in the northern hemisphere? People were very surprised when they finally flew a mission and found out that it was trying to make an ozone hole, but it never does for a number of reasons. But it was really a scientifically exciting period. And the ozone hole is still with us. I know it's pretty bright here, and you probably can't see this that well, but this is just showing you what the ozone looked like in 79, and then 2006, biggest one yet ever. 2013, somebody even wrote a paper saying it was going away. 2014, it's not going away. This is meteorological variability. It's going to happen. This should go away in about 2060, and so you all are empowered to check. And when it's gone, you can go, wow, I heard that when I was in school, and check. So one of the features, and I just put this up because this is showing how well we can do with a model. There's a picture of data that looks just like this, and I don't know where it is. I was shocked that I didn't have it. But what you're seeing is that inside, like the area where the ozone is low here, or that's potential vorticity, this is showing you the vortex boundary. So if you're outside the vortex boundary, you have some pretty high values. But when you're inside the vortex boundary, you're seeing this deep descent. So air from the mesosphere actually comes like swoosh down in a big cone as the vortex spins up. And nobody knew that was happening, and that's an essential part of forming the ozone hole. And then when UARS finally was in air, we got some pictures that show you pretty much what's happening. I don't know how well you can see this, but this is the lower atmosphere. This is CLO. That's the radical that does everything. This is the nitric acid, and you can see that's very low, and that's important because if it weren't low, then the CLO would react and it would make chlorine nitrate. You see it makes chlorine nitrate in a ring around, but not in the middle. And then this is the ozone showing you the very low values. And then you can see the difference in the hemispheres here, where you see almost no CLO, where you see lots of ozone, you see lots of nitric acid, and you see the polar vortex filled up with chlorine nitrate. So you really do understand why it happens in the southern hemisphere and it doesn't happen in the northern hemisphere, because there's differences in the composition and the temperature and the stability of that polar vortex that keep it from happening here, which would actually be bad for Minnesota, frankly, if it happened. You wouldn't want that to happen. Okay, now here we have a little movie, if the movie works. So this shows you some data from Aura. So this is pretty cool. This other person wrote a theoretical paper that said that what you're going to see happen should happen, and then I was able to find evidence of it happening in the UARS satellite data, but UARS had this thing where it would turn and look at one hemisphere and then turn away, and it would turn away every time things got interesting. It was kind of set up that way. So then finally, when we launched Aura, we were able to see the whole thing. So if you put it on, we're going to run through it once, and then I'm going to tell you what to look for. So here we have Antarctica, and this is the cold temperatures, very cold. The white line is the polar vortex boundary. That's chlorine monoxide. That's what's doing the stuff. This is nitric acid being low. This is hydrochloric acid, and this is water vapor, and here's ozone. Now it's going to go through again. Ozone's already low here, but it's going to finish this, and then it's going to go back. There. So ozone's pretty high, and there's no hydrochloric acid. Now as ozone gets low, you're going to suddenly see this just fill in with red. So that's like pretty awesome, right? That happens in just a couple of days. It happens because once the ozone is low, usually what happens is Cl reacts with ozone and makes ClO, and that's a pretty fast reaction. But once ozone is low, the Cl can't do that anymore, and so it builds up in the polar vortex until suddenly the time scale for making methane from Cl plus, or for making hydrochloric acid from Cl plus methane becomes really short. So you see this reaction that nobody ever thought would be important happening and changing everything in a course of days. If you notice this after the hydrochloric acid happens, there's no more chemistry going on. The ozone just stays low. It's just going to stay low until and the ClO is gone, and it's just going to stay low until the dynamics breaks it apart. But the chemistry is done. But that's also why the ozone hole is going to be with us for a long time, because we run out of ozone way before we run out of polar vortex. So what will happen is the minimum will just happen later, but it's going to keep happening for a really long time. Okay, that's it with the movie. Thank you. That worked great. I tried all last night to find a copy of that movie I could embed. Couldn't find it. Okay, now all that's really leading up to, we want to improve assessments. We have these assessments. The World Meteorological Organization, the UN, we do this scientific assessment of ozone depletion. We do it every 4 years. It's part of the protocol. You have to do it. It's a requirement. So every 4 years, you have a presidential election, you have the Summer Olympics, you have the World Cup soccer, and you have an ozone assessment. Those things happen. And they punctuate your life. There's no way to get around it. It's a driver for model development. It's a driver for using the data to evaluate models. Many nations have models. Everybody can participate. One of the cool things about NASA data is that now it's open access. For UARS, there's an 18-month rolling protocol where people had private access. For European missions, people still have private access for some number of years before you can get data. But the NASA data is public as soon as it's retrieved. As soon as they've taken the radiance and retrieved it, the data is out there. So that has really changed the scientific landscape. The person who thought of that was a visionary. This is just a schematic to show you about the stratosphere. Here's the ozone layer. This is the general circulation. Source gases come in the tropics. You have a lot of chemistry going on in the stratosphere. How does the photochemistry work? This is going to be quick. This is the basic Chapman cycle, where you have production and loss of ozone. You break apart O2 to make O atoms. We call that odd oxygen. They react with everything. They're very unhappy, and so they'll react with an O2 in the presence of a third body to conserve momentum and energy. To make an ozone molecule. The ozone itself is pretty unstable, and it just destroyed by UV. So these things happen. These two are slow. If an O reacts with ozone, that's a net loss of odd oxygen, but these two just switch things back and forth. And between those reactions, everything would be really simple if we didn't have the other gases. So we have source gases. These are gases that are stable. You can think of them as protected by the ozone layer. People think of CFCs as bad things, but when they were invented, they were great, wonderful things. You breathe them in and out. They don't react on your skin. They don't give you a rash. And they refrigerate really cheaply. So they were wonderful molecules. It's no wonder everybody was using them, because they were replacing far more dangerous coolants in refrigerating systems. But they are protected by the ozone layer from falling apart. They're stable molecules. They have to get above the ozone layer to break apart. Some of the replacement compounds, the way they make a replacement compound basically is that they add an H onto it somehow, or more than one H, and then they'll react with OH. That's a mistake there. And they also produce chlorine radicals. And then water is a key player in all kinds of chemistry, and it reacts with O singlet D, and you get hydrogen radicals. The reservoir gases are there to interfere with things. I've mentioned them already a little bit. Hydrochloric acid, so that once you've put a chlorine into hydrochloric acid, it's not reactive with ozone. Once you get your OH and NO2 into nitric acid, they're not reactive. Once you get ClO into chlorine nitrate, it's not reactive. So how much of those reservoir gases are and the balance between them and the radicals is what really controls what's going on. And then the last thing you need to know is that these losses are catalytic cycles, because the chlorine is parts per billion, ozone is part per million, and the way that you can actually affect the ozone amount with something that is present and 1,000 times less, you have to have a catalytic cycle. So you have ClO plus O making Cl plus O2. Cl immediately reacts with ozone, making ClO back and O2. So the net of this is just the basic loss reaction. And there are many cycles of this sort. So ever since I started working at NASA, I've been working in the assessments. A group of people agrees on what the boundary conditions should be, how chlorine is going to change, how the source gases are going to change. You get required simulations, you work like crazy to produce them, and you either put them in a repository and someone analyzes them, or sometimes you get to be the analyzer, and now and then you get to be the author. I was a lead author in 2010. It's a big job. And this is what assessments look like, and this is just to show you how awful things can look. This big decrease here is Mount Pinatubo. This is 1998. These were 2D models. None of them have climate feedback, and so everything is negative, okay? 2002, some of them have climate feedback. Things are positive. We're still going down for Pinatubo. 2006, we're 3D models here, 2D models here. Everybody has climate feedback, but these models are all over the place. And I would have a hard time saying we had any certainty in prediction. The other thing that you see here that's really interesting is that the models all stay together with the data when there is data. And as soon as there's no data, boom, they fall apart. So you might wonder to yourself, what's up with that? These are just profiles. In the interest of time, I'm not going to stick with the profiles. It's really the same point. So you can think about this, the different assessments. First of all, comparisons with observations improve on a 4-year time scale. Every 4 years, we do get a little bit better. The time series do bunch together when we have the observations. They diverge thereafter. And this good agreement for ozone between 1980 and 2010 tells you absolutely nothing about the future response. You might think, why is that? I have an answer. Part of it is that there's a human element in model development and evaluation, and I've experienced this, so this is really true. If a diagnostic is so important that you have to get it in the model, you will mess with the model until you get it. Okay, but you might not be getting it for the right physics. You might have affected something else in a negative way, but you will get this. You will get good agreement. And so if you have to get it, you will get it. But as soon as that happens, the model, that diagnostic becomes useless for the whole group. And I've experienced this happening more than once. And so then as soon as this happens, you have to think harder and come up with a better diagnostic. It's kind of why I say modelers, it's like doing you've got this bar and you've got to jump over it. And you do jump over it, but then the next time you come back to it, they have raised the bar because of the way that this process works. So the challenge remains. We want to try and figure out, what can we do? Because this is a hopeless situation, to really connect the simulated response to the diagnostic. So there is an international group. It was Spark CCM-Val, and I'm going to keep calling it that because that's what it is in this context. It's got a new name now, CCMI, and then it's going to add aerosols like in 2 weeks. Then it's going to be CCMI plus, I can't remember the aerosol acronym, but we're moving it forward. But our goal is to improve understanding of the CCMs through what they call process-oriented evaluation, with the hope that by showing how well the processes are represented, you can connect them to the projection. So in the 2010 Chapter 2, I was the lead author of Chapter 2, we actually did this a little bit. So the black here, which you can see, is the merged ozone data set. This is just the period, 1980 to 2010. The reds are the models that actually have excellent ratings in some of this process evaluation. And so you can see that they really do follow. One of them is missing a solar cycle, so it doesn't go down and up. That's this one. So we know why that one doesn't do this. So we're kind of like, wow, that's really pretty cool. But we did not really explain why transport generically says this assessment is better. We only said transport is better. So we were missing something. And again, this is the same thing with the profiles, where you've got some observations, and you've got the better models, and you see you lose out these ones with really big changes that are outliers. And you kind of think, well, maybe we're making some progress here. And then this one is the same as the previous one, and then this one is showing the future. So not much has changed, not much is expected to change as we move forward, because the chlorofluorocarbons are decreasing at only 1/3 the rate they increased. So if it took 13 to 15 years to see a signal of them increasing, how long do you think it would take to see the signal of them decreasing? Let's go with 30 to 45, okay? But we keep looking anyway. It's like an industry. People are really trying to find this. And then you say, well, so much about the past. What about the future? When you look at all these models and we're looking for the future, you can see that we really do diverge. But and these are done by latitude. This is the tropics, this is the northern mid-latitudes, this is the southern mid-latitudes. This is a 60 to 60 average. But you can see that the models with good transport, put that in quotes, do cut down and remove some outliers. And I wrote this paper with my colleague Susan Strawn, so we were pretty excited about this. But we hadn't done everything. In the end, this is a weak statement. To say better transport makes a difference is true, but we have to be able to connect it to the loss processes to show why it's true, and how better transport works. So I took all these different model simulations, and I used the strategy of treating each one of them like an actual atmosphere and trying to understand if its behavior made sense in the context of saying, okay, this model represents a real atmosphere, and I have sort of some underlying physical and chemical concepts of how it's supposed to work. Is this the way it did work in that model? And can we understand why the responses are different? So this shows you an example. You can see these two models. I can separate the chlorine response from the climate response, and these two are very, very similar for their response to climate change. That's the line, and both of them 7 and 6 Dobson units. That's pretty good. But they certainly were very, very different in their sensitivity to chlorine. And here's a couple more, and their change for chlorine is very similar to each other, but their change to climate is very different. So you're starting to make some progress here in understanding where the sensitivity comes from. Oh, there, that shows the climate contribution. I forgot I had to click twice to get the number on there. So they look similar for chlorine, but different for climate. Now, when you look at them all together, what you're trying to do is understand why do they have different sensitivity to chlorine. And we use what's called mixing ratio boundary conditions for the source gases, so we should all be doing the same thing. But if the circulation is different, the actual amount of chlorine that the model puts in the atmosphere is very different, because the surface acts like an infinite source. So when you compare, this is to measurements from the NDAC, the Network for Detection of Atmospheric Composition Change. It's an international effort also. So this is Karuna, Harastrua, Jungfraujoch, and Kitt Peak. So like this one's US, this one's in the Alps. This one's Norwegian. I forget who runs this one. They might both be Norway. So we've been making these HCl measurements for a really long time. This is all the models that do not have good transport, and these are the ones that do. So you think, okay, I've got a clue. The models with good transport are doing a good job on the reservoir gases. So that's really your key result. If you have better reservoirs, it means you're going to have better radicals, and you need the better radicals so that you can have not just the loss correct, not just the total, but each contribution has to be correct so that then when you change one, the change is in the right relative amount. So moving forward on that, I looked at chlorine nitrate, which is more directly to CLO, and these are measurements from the Canadian instrument ACE, which is a Fourier transform spectrometer. And what you can see is that the chlorine nitrate to CLY ratio is actually almost linearly related to the sensitivity to chlorine. So now we have done what we set out to do. We have made a link between the processes and the transport, and we understand why transport makes a difference in connecting and in connecting what the projection is to the model behavior. So here's a little scientific summary of what we learned. The basic principles that we developed in the 80s to understand how the ozone will respond to the perturbation have stood the test of time, and they're really useful in analyzing the behavior of this ensemble of models. There's 14 models in this group. I think that was the 2010 group. There was more than that. And of course, this is the same challenge that is faced for the IPCC when they're trying to do the climate change projections. These principles of the rate-limiting steps and how the radicals and reservoirs react with each other and interact with each other explain why the CCMs have different responses. They show you how the simulated response is a function of the simulated base state, and why good agreement for simulated ozone does not discriminate among them, because that good agreement for simulated ozone doesn't say that the loss processes are in the right proportion or that the transport contribution to the ozone is in the right proportion. So you're able to mess with the model in such a way that you've changed both the chemistry and the transport in a way that produces that ozone plot, but it leaves other aspects of the chemistry sort of out to lunch. So that's why in looking at the system, you had to have measurements of ozone, but you also had to have measurements of the separate radicals so that you could be sure that the whole system was behaving correctly. And so when you put it all together, you can see that the good agreement that you need for ozone and for the source gases, that's going to give you the right dynamic contribution to the ozone tendency, and the reservoir gases and radical gases. And you really need to look at the entire system. You can't just look at one part of the system. And again, this is partly why the earth science tends to be done, by groups of people, because different groups of people are experts in different areas. And so, like, the best thing that can happen is when you've got a chemist and a dynamicist and a radiation expert, and they're really working together, and they're not just polishing their own piece. Because another thing about the models is, like, because they have so many pieces, you can make this part perfect. But if these pieces aren't perfect, it's still going to be a junky model. So it actually works better if none of them are perfect, but all of them are good. And that's something you can think about too. And then I was going to give you a career summary. I have been fortunate in many ways. And I think one of the most important things for me, I was fortunate to have really excellent mentors. My high school math teacher In college, my physics professors and one of my math professors were just awesome women who really, really did push me forward and open my eyes to the world and what was possible. Because I really hadn't been raised to think much of anything was possible. And I'm not blaming my parents on that. That's the condition they were raised in. It's just, I had no idea. I mean, an example of I had no idea, even when I chose environmental science, that I was going to be involved in international projects. So I've been fortunate to go to Australia and Europe and Japan and all over the place. I had no idea I was going to do that. I was shocked. So it was fun. But I also had really good mentors. Okay, so I did high school, college. In grad school, I can't say enough about some of my professors, one at University of Minnesota in particular, and then my major professor at Iowa State, because Iowa State hadn't graduated a woman PhD in about a decade. They would get one every year, and she would drop out. I mean, no, and they would come, people would come and tell me about her. You know, like they would come and they go, oh, we had this woman, you know, and she did this, that, and then she dropped out. And I'd be like, what? You know, like, so I ultimately realized I was like symbolic as well as an actual person. Even the department chair, once I had passed the orals, and I was struggling because I had had the fourth baby, who's a little gift from heaven, and I didn't know how I was ever going to finish, but he used to like come and give me pep talks. It's like, you've passed the qualifiers, you have to finish. I don't think most students get that kind of thing. You know, so I was fortunate that I had those people giving me a little push. And I was really fortunate at NASA. Rich Stolarski, you could have ever heard of, maybe, if you follow the ozone problem, because Stolarski and Cicerone were the ones who proposed the catalytic loss for ozone involving chlorine, and then Rowland and Molina built on that and had the source for chlorine in the stratosphere, and then everything changed from there. So like Rich was that close to the Nobel Prize. But Rich Stolarski taught me chemistry. So it's awesome to have people in your lives like him. And then ultimately, I have to say, deciding to work in environmental science was a good decision. It's in some ways, it's a tough decision. Like compared to space science, not that I don't love the space science part of NASA, believe me, I do. But they get beautiful images, and they get to show them, and they get to give press conferences, and everybody goes, oh, wow, that's awesome. You know, we figure something out, and we say, you're going to get methane being released from the permafrost, and that's going to exacerbate climate change, and New York City's going to sink. And everybody goes, I don't want to talk to you. You know, like, they don't have any of that. And that's the hard part with earth science. And the other part that I learned, speaking to the press once, I was young, and I hadn't been to media training, and people were still worrying about whether Mount Erebus, a volcano in Antarctica, was creating the ozone hole by injecting chlorine into the lower atmosphere. And we had some pretty conclusive proof from the UR satellite that it was not. It's not pretty conclusive. It was very conclusive. And so we gave a press conference, and the press people go, well, this is really interesting data, but are you sure it's not a volcano? And we'd explain. This is after the press conference is over. They come up and they surround you. Are you sure it's not a volcano? And I go, yeah, we're sure. And we explain it again. And they go, well, that's really interesting, but I just don't get it. Are you sure it's not a volcano? And they just kept saying it. And I finally go, truly. And I say, we've got this nailed. And as soon as I said that, they all left. And then one of the program scientists from NASA, who was older and wiser, he says to me, well, how does it feel to be a media star? And I said, what? Well, we've got it nailed was on the front page of about 25 or 30 newspapers. It was all over the internet. It was like, I was a media star. And I was like, oh my gosh. Well, what that gives is the people on the other side a chance to shoot at you. So then they all send letters to the editor, and then you have to answer them. And then they call you up, they send you email, and you've got to respond because you work for the government. And you have to be polite to citizens, even when even when they have nothing to say. They want to know if the fluorine could have come from toothpaste and if the chlorine came from swimming pools. You know, like, and you go over and over this stuff and you think, I don't want to talk to anyone. I don't want to talk to anyone. Even with that, I still think choosing environmental work was a good career. So yeah, I'd be happy to answer any questions you might have.
Thank you very much for an inspiring talk. Let's thank our speaker again. Questions?
Hi, thanks. Aura, I'm thinking gas, and then I think I heard last night, was it Aqua and Terra? I'm thinking water and earth. How much do you interact with maybe, water scientists and maybe solid and earth scientists? And what I'm thinking of is you're kind of thinking about going forward with the atmosphere, and I'm thinking of ice core samples that go back and attempts at the atmosphere from years and years back.
Well, okay, so when you're trying to do the climate projections, you're looking for data wherever you can get it. And so one of the things that you do in the atmosphere is you have to do simulations of pre-industrial atmosphere. And so you do make connections with the ice core people as to what the composition was, how it's changed. I think if you were to read or look at some of the papers from the model at GISS, the Goddard Institute for Space Studies, where Jim Hansen was the director for a really long time, you would see that they have done a whole lot with that aspect of modeling. We tend to be, and this is political reasons too, 1960 and forward, but we do interact with the scientists who are working in other aspects of the Earth, because in the end, what I'm talking about here, the chemistry climate model, so it isn't a full climate model yet because it doesn't have a coupled ocean. You have to have a coupled ocean. And so we are moving towards the Earth system model. So when we have the Earth system model, we have to be interacting with the oceans, with the land surface, all those different, with the hydrological cycle people, all the different disciplines. It's one of the fun parts of being at NASA because all of those people are there. We also see collaborations with scientists and universities who are interested in who are interested in putting their ideas into a global framework. And we also have a lot of student internship programs. You should check them out. Aura and Aqua are in the A train. Has anyone heard of the A train? It's a constellation of satellites. Aqua isn't first anymore. OCO is first. But they fly in formation. They're about 9 minutes from the first one to the last one. And so you have the opportunity to see clouds and aerosols and composition and some surface stuff, boom, boom, boom. And then you can really put it together. Probably the Aura scientists have done the most with the aerosols and clouds. We're looking for impacts of cloud and polluted clouds and precipitation and that kind of thing, and how that's one of the indirect effects is how aerosols affect clouds and composition.
Hi. So my question for you is it just the wish to teach that drove you to go from master's into a PhD program, or was there any other reasoning behind that?
Oh, no, that's a really good question. I actually thought about saying that. I started out in a master's program. I was with Mark Ingebretson, and he was going for a PhD. I was going for a master's. I was intending to get a master's with all these boys at University of Minnesota, and practically every day one of them would say to me, "You don't have anything hard to do because you're just getting a master's." They said that to me about 9,000 times. And ultimately, I would say I went for a PhD out of spite. I was like, I'm as good as these guys, so why am I just getting a master's? What's the matter with me? I can finish a PhD. And so I did. So that's a good question. Thank you for asking it. It's a different environment for girls now, though.
You said that every 4 years there's an ozone depletion. I was just wondering, when's the next one? I mean, ozone assessment.
2018.
Okay.
We just did 2014.
Right. So, thank you.
The Montreal Protocol is pretty cool. It's probably worth saying a few words about. So it's this major environmental treaty. Every country has signed on to it, including like the Vatican. Everyone's signed on. No one is not in it. And the countries meet every year. The parties to the agreement meet, and they want to know what's going on, how it's going. Any controversy that's brought up, they want to know about it. And the interesting thing that they're thinking about now is that many of the replacement compounds for CFCs are greenhouse gases. And so they're trying to figure out a way to not have the good that is done by eliminating the chlorine threat to the ozone layer turn out to be a worse threat to climate change.
Hi, thank you very much. I would like to know more about what's being done in K-12 science education. I remember participating in a number of NSF workshops in the early 90s on ozone curriculum, and I haven't seen that lately in the K-12 curriculum, so I'm wondering if there's much interface these days with the K-12 system to really take some of the research there and translate it back into high school and even into middle school curriculum. Thank you.
Okay, we are kind of in flux. It's pretty interesting. Every project used to have a K-12 requirement or an education and outreach requirement where we had to spend 1% of our total project funds on education and outreach. And then someone in the government noticed that more than one agency was spending money on education, and they decided the education should only be done in one place. So at this moment, NASA, through our projects, we're not allowed to do education. We're only allowed to do communication, which means they have taken us out of curriculum. And so we're kind of in flux at this point on this subject. It's an interesting interaction with politics. There has been a lot done on K-12. And we certainly have teachers come all the time for workshops. But I'm going to say NSF has more freedom to do that kind of stuff right now than NASA does, and I don't really know what's in the works.
If I can ask a question, what advice would you give students who are considering entering this field and in the future possibly following graduation or for graduate school?
Well, what I tell, all right, I'm going to use my daughter as an example. My daughter, who's the mother of quadruplets, is an oceanographer. And I encouraged her and would encourage anyone, frankly, to get their undergraduate degree in a hard science because it's just better. It's just better. You really need depth in something, and I think it's really important to go for depth in something. But then there are lots of summer programs. Like she wanted to know, do I want to be an oceanographer? So she was able to get in the summer program and do some ship work and all that kind of stuff. So that turned out really well for her. We have summer programs. I think, various NASA centers and other institutions have summer programs. You have an opportunity to try out and interdisciplinary science, which, what I'm really talking about here is interdisciplinary science. You have an opportunity to try it out at the undergraduate level. And then when you go to graduate school, you look for a really good, strong graduate program where maybe you're going to see what's your specialty sort of being very strongly integrated with some of the other areas of earth science. So that's how I would try to go about it. We have tons of stuff about, like the scientists and what's going on at NASA that's easy to find on the web. So if you were interested in moving forward in environmental science, you do a little homework, and then even there's two ways you can hear from students. One is they send you a note and they say, I've got a senior project, basically, will you do it for me? Those people don't even get responses, honest and truly. I don't reply to that kind of note. But when you get a note from a student and they say, and this is true, I think, for your government scientists in general, and they say, well, I read this, and I learned this, and I learned that, and I want to know about this, you're going to start an interaction, and that could be really good for you, too. So I think you have to be proactive in pursuing, getting some communication open and seeing what you can learn.
Hi. Sorry. I'm wondering, what do you think is the most important thing for an elementary teacher to teach their students about environmental science?
The most important, in a specific scientific way, I can't think, I'm not going to give you a really good example, but I think that if they learn how things are connected and that you should never waste anything and that you should sort of think twice. I think that many of the problems that we're dealing with now when we look at the environment are because people move forward with something because it made good economic sense, but without thinking twice. And so I would be trying to teach young children just how things are connected, like how the flowers need the bees and what the rainfall. I think the water cycle is a really fun thing to teach kids about. Because all the kids love clouds. And for a while we had a program at NASA of cloud observations because we were using school children in validation of some of the remote instruments of clouds. So they were supposed to go out at lunchtime every day and look up and then this is fun, and then fill in on a little web thing what kind of clouds were over their location that day. People can get really interested in that kind of thing. Everybody wants to look at the clouds, and a lot of kids get pulled into, weather, the weather enterprise. People are so interested in that, and that's a good starting point for getting into other connections. It's the connectedness that I would want to teach school children.
Thank you.
Okay, well, it looks like do we have any more questions? Okay, if not, let's thank our speaker again. Thank you so much.